Hello, my name is Alvaro, and I am a PhD candidate at the University of Colorado Boulder. Today, I am in Chicago at the APS March meeting, and we are presenting in a couple of hours this paper where we study the growth and detachment of axisymmetric bubbles when they are subject to inhomogeneous magnetic fields in microgravity. As you know, my research deals with the dynamics of liquids microgravity, which is an scenario where surface tension adopts an overwhelming role over buoyancy because due to the microgravity environment, the buoyancy acting on multi-phase flows is interesting, but also extremely complicated, in particular for electrolysis applications. It happens that when you have two electrodes or two boiling surfaces, in general, any kind of nucleation surface in microgravity, it will start generating bubbles that will generate a froth layer over the surface of the electrodes. And that will hamper the efficiency of our mechanisms and also induce problems in terms of phase separation. So in order to assess this, some time ago, we came up with this idea of using magnets and diamagnetic forces to detach those bubbles from the surface of the electrolytic cells and collect them. And in this way, we can combine two functionalities. The first one, we can detach the bubbles from the cell, in improving its efficiency, and we can also collect those bubbles, submerge them, and induce phase separation. However, there are some very fundamental and interesting questions to be assessed here. The first one being, what is the bubble departure diameter in the presence of a magnetic force? What is the shape of the interface? And which are the natural oscillation frequencies of these systems? And that is important because if we know the oscillation frequencies, we can also excite the detachment of bubbles by means, for instance, of electric fields. This problem, in fact, is relevant on Earth when studying the detachment of bubbles in ferrofluids, because ferrofluids are highly susceptible materials that we can use to study this phenomena. But the problem that we face is that this is a coupled fluid magnetic problem. We cannot solve the Navier-Stokes equations without considering the solution of the steady-state Maxwell equations. So in other words, we need coupled fluid magnetic simulations to assess this problem. And we could of course neglect the use of ferrofluids and simplify significantly our framework, but that will restrict the validity of this simulation. And we wanted to assess the full problem because it has interesting applications in other fields, like for instance, electrohydrodynamics. So we developed this numerical simulation framework, whose fundamentals are described in this paper by Professor Herrada and Montanero. And here we present as a symmetric geometry, loads and boundary conditions. We divide the simulation domain in three regions: the fluid domain, the bubble, and the solid substrate. And we use second-order finite differences to solve the full fluid magnetic problem with a monolithic, fully implicit Newton-Raphson approach in a single time step, which makes the method particularly efficient. And also we solve, since it is monolithic, we can solve the fluid and magnetic equations simultaneously. And this has advantages because it allows us to not only compute the bubble equilibrium surface or interface or the departure volume, but also the stability properties and natural frequencies of the system, and of course, time-dependent simulations. The governing equations of the problem look like this. We have the mass balance and the momentum balances, where we have the source, the magnetic source terms here in these red boxes. But at the same time, we solve the Maxwell equations, the steady-state Maxwell equations. Now, in order to do that, we divide the magnetic field H according to the Helmholtz theorem into two potentials, a potential function and a current function. And it turns out that when you run that kind of division, one of the potentials is completely uncoupled, and that potential is the one that determines the magnetic source. So in our numerical simulation framework, we detach completely the magnetic source from the system. And in this way, we are able to simplify a lot the meshing of the problem. You can find further details in this paper that is currently under consideration. In terms of results, what we find is something like this. So here we are simulating this kind of magnet. It is a 2 centimeter radius, 1 centimeter height, a neodymium magnet that we magnetize at different levels. In this case, a very small 10 kiloamperes per meter. You can see here the magnetic fields that looks okay for this kind of system. And at the right, you will see the magnetic force. And there is a qualitative difference with buoyancy forces, which is that the magnetic force depends on the distance to the magnet. So you can see that it is very strong at the bottom of the system, but very weak on top. And there is another characteristic, which is that here in this corner, you will see a very strong magnetic peak caused by this corner geometry. That is a problem from the numerical perspective, because that is effectively a singularity that we need to assess very carefully and that we are treating right now by modifying the density of the mesh in that region. Here I show some preliminary or illustrative results of the equilibrium of different bubbles with different contact angles. I say these are illustrative because these results haven't yet passed the test of the mesh stability or the mesh density stability analysis, and the validation of these results is ongoing. I'm just showing them to show you what kind of capabilities our code has. So you can see how different the results are. In the case of 30 degrees, the increase of the magnetic field pushes the bubbles, flattens the bubbles close to the surface. In the case of 90 degrees, it is the opposite because the magnetic force is stronger at the bottom of the bubble. So it squeezes it and elongates the bubble. And the same happens at 150 degrees, but in this case, the inflection point of the curvature is different. It is displaced to the top, as you can see. As I mentioned before, our code is monolithic, which allows us to compute the frequencies by linearizing the problem and computing the eigenvalues of the linearized Jacobian. So what we see here is that, and this is what we saw here the first time we analyzed this, was that for 30 degrees, there was a point where a dynamic non-equilibrium solution was produced. And this dynamic non-equilibrium solution is produced when you have an imaginary frequency or damping that is positive. However, we think this is actually caused by a poor meshing of the bubble, and we are working on different solutions. But it will make sense that this particular case, the 30 degrees, presents this kind of instability, because as you can see here, the bubble is very, very closely attached to the magnet, and as the bubble oscillates, it reaches regions where the magnetic force is much stronger, which means that it wouldn't be surprising to find such a bubble that when it starts oscillating becomes unstable just because of the configuration of the magnetic force. That will be interesting because most of the instabilities that we see here have a zero real frequency, meaning that it is just an unstable mode that breaks the surface. In the others, you can see how the increase of the magnetic force of this bubble immersed in ferrofluid increases the real frequencies mainly, and also with the imaginary frequencies, meaning that the bubble starts oscillating much faster. Finally, I present here the results for DI water, which is a weak diamagnetic material. In this case, we can reach much stronger magnetic forces because the water is much less susceptible than a ferrofluid. So you can see how the frequencies in this case diminish because the force is pushing the water away from the magnet. And that is very interesting. On the contrary, the equilibrium surface is almost get completely the same. It is almost invariant with the magnetic force. So this is a work in progress. We are working on mesh refinement, on making the system more stable, on making sure that things are properly done and that we can validate these results. But this preliminary data set shows you what kind of capabilities this code has and how powerful it be and how useful it can be for studying the new applications that we have in a microgravity environment in terms of space technology. So thanks for watching this short presentation. I would like to acknowledge the APSG, La Caixa Foundation, and the Spanish government and Andalusian government who have sponsored this work. Any of these links or send me an email, and we will be more than happy to answer them and collaborate with you if you think that useful for your watching this short paper.